What's up? What's up? I don't know what this intro is. Okay. So what's up, people? It is the 31st of August because there are 31 days in August, I'm pretty sure. Yes, okay. We're correct. So this means we're learning hash table today, the data structure in Java, because why not? I just had a great morning because I was out on my morning bike ride and I was like, I'm gonna see if I can ride my bike with no handlebars. I was able to. It was I was able to. It was really cool. So I can do that now, and that took me a morning, which is crazy because it's like I didn't think it would happen in a day, but or in a morning, I guess. Anyway, that's beside the point. Here we are learning hash table, I guess. Let's begin. We have a class declaration called a hash entry. Also, the where I got this code from, I will link in the description. So I will make that a note at the moment. Link description with hash. Okay. So on line 1, we have a class declaration of a hash entry, and then within this declaration of a hash entry, we have two members called a key and a value, and they're both private and they're both integers. Obviously, these could be any kind of data type. However, I remember reading in a textbook about how key values should always be integers because the lookup time is constant and less there's less of a chance for collisions. Anyway, so we have these two members, and they're two members of the hash entry class object, I guess, or class. Yeah, class. And then we have a constructor, which pretty much takes the values that you put into the keys and values, and you assign them, you construct them, the hash entry object with them, and then you have a getter for the key and a getter for the value. So now we move on to the class declaration of a hash map, which this is the table, I guess. So what happens is the way a hash table works, the search, insertion, and deletion big O of it are all constant. And why is this? It's because a hash table takes up a lot of memory in exchange for constant lookup times, which is great depending on your situation. But an average case of constant time for all these, for search, insertion, and deletion, are really good because if you have a database, for instance, and you use a hash table for your database, you can look up entries in constant time, which is amazing. So now, worst case, when I first saw this chart, I wasn't sure how a hash table could be O of n, a big O of n, because it doesn't make sense because in my head I'm thinking hash table as in a appropriately implemented hash table, where everything hashes to a different spot every time, and that's the goal of your hash table. It should be big enough to where everything's constant time. So I was trying to think of an example to explain the worst case. If you think about it, a hash table that is big O of n would be a hash table that is poorly implemented or has a small, the size of the hash table is not accommodating to the amount of entries you'll have. So I guess what I'm trying to say is, if it's big O of n, it'd be essentially an array, or a vector, or however you want to think about it. So essentially what it means is, if you had a poorly implemented hash table, and the hash table is, for instance, some stupid hashing algorithm where everything hashes to the same spot, let's say you use a hash table with a linked list or something, and what happens is, let's say you hash something to bucket 27, and so when you get to bucket 27 and you try to hash another, you try to place another element into that bucket, into bucket 27, and it makes a linked list in bucket 27 to reference everything after that bucket, instead of table doubling or resolving the collision or whatever. That would be ON, because if everything hashes to the same spot, then you have to go to that spot and iterate through n elements until you find the element that you're looking for with the value that you're looking for. So let's say in bucket 27 you have 10 elements in bucket 27, and one of them has a value. All of them have unique values, but the same key value. The same key, because that's confusing to follow. So let's say every 6 elements have a key of 6. Actually, you know what? Let's write it. So you have a hash map called map, and you're constructing it. Hash map, and the constructor in the class declaration is a table size of 128. So let's say you put in 27, and this is not going to be exactly the same. Let's say you put in, what did I say, 27? 26? I will do 6. So let's say you have 5 elements, all with 6, and come on. And what happens, so this, and we want to print that, so not that. Okay, so what I'm trying to explain is big O of n for a hash table, as seen here. And just really quickly, space complexity of a hash table is obviously O of n, because you have n elements in your space, but the space is really big, so there's some trade-offs there. But anyway, so worst case of big O of n for a hash table would be, the way I'm going to explain it is this way, which everything hashes to the same spot. So let's go to the put function of your maps, which is up here. So then you have your put, and you have your key, and then you have your value, right? So key and value, and it's hashing it, and then it looks for an empty space, and that the key does not already exist. See, this is kind of ambiguous. It's like, it's not the most sophisticated hash table implementation, but it's simple enough to understand the structure, the basic structure. So in this put function, what's going to happen is when you have a 6, when you try to put in a key of 6 and a value of 10, you're going to you're going to make the hash, and then you're going to find the bucket that you can put this hash into, the elements to put the key value combination into the table, if that makes sense. It's really, I feel like that's hard to follow, but so what happens with this line 63 to 67, what happens is, regarding this particular put function, what's going to happen is you have you have a key value of 6 and a value of 10. So then when you get to whatever bucket that the 6 hashes to, you're going to put in 10. And then for the sake of the big ON search, insertion, deletion of a hash table, let's say that when you get to the second put function, this put declaration function, you get to the same place as you did before with this key of 6, the key value of 6, and when you try to put in 11, instead of resolving the collision as moving over in the hash table, you stay within the hash table's bucket, wherever this 6 hashes to, and then you would make a linked list beyond that bucket to show that you are linking. It just so happens that would be a stupid. Oh, that'd be so dumb though. Because why do you want? What's a good example of hashing, purposefully hashing multiple elements to the same bucket in a hash table? Because unless in the hash table that you've thought up, it would be something like, let's say you're making a database of people, of like a contact list. So then if you hashed, let's say you hashed my name, David, to a bucket, and then you would for some reason want someone else to hash to the same bucket. Let's say, okay, so let's say there's a family or a group of people, and you associate the names of a certain bucket. See, but that doesn't make sense because it's random. You would want the. That's kind of dumb. Why would it be O of n? Wait, why is hash table worst case 1? So let's read. I can say different type complexities for these functions on the half table. In some course notes, including O1, using hash tables, can expect. Okay. Hash tables are O1 average and amortized case complexity. However, it suffers from ON worst case. Hash table suffers from ON worst case due to 2 reasons. If too many elements were hashed in the same key. I was right. Okay. So once the hash table has passed its load balance, it has to rehash, create a table doubling. Okay. However, it's said to be O1 average is very rare that many items will hash the same key, because if you have a good enough if you have a good enough hash algorithm to where each key is unique consistently, and you can account for collisions in an appropriate way, then you should have a decent running hash table. The rehash operation, which is ON, can at most happen after n over 2. Operations which are all assumed O1, thus when you sum the average time per operation you get n of O1 plus On over n, which is, okay. So he's just proving when you, the On of the big O of the rehash operation. Note, because the rehashing issue a real-time applications need low latency should not use a hash table as a dish. Latency is a delay from input into a system to a desired outcome. The term is understood slightly differently in various contexts, and latency issues also vary from one system to greatly affects how usable and enjoyable electronic. Oh, latency. Okay, that makes sense. So like between, like, let's say frames of a video game, you want the latency to be very low so that it runs seemingly smoothly. I say seemingly because it's like moving. Video games are just moving pictures, but they're so smooth in their transition from picture to picture that it simulates movements. Anyway, let's read this. Another issue where you might see a performance loss in large hash tables is due to cache performance. Hash tables suffer from bad cache performance, and thus for large collection, the access time might take longer since you need to reload the relevant part of the table from the memory back into the cache. Oh. Interesting. Okay. Hash table is O1, okay, it's the same thing. Okay, so yay, we learned. So ON, so I was right. So imagine if you had ON, back to the family example. If I had my name, David, and my, let's say, let's make fake names like Lisa and, well, not fake, but, you know, example names, Lisa and Corey. So let's say it's me, Lisa, and Corey, and we all hash to the same bucket for whatever reason, because that's a poorly implemented hash table. Then, if you wanted to search through this bucket itself, you'd have to go through n elements to find, let's say, Corey's hashed to the, let's say, this is me, David. Oh, excuse me. Corey. let's make two more. Poop and foo. Yep, because those are names. So let's say we have, I hash to the first table, I hash to the bucket first, and then I have Lisa hash to the same bucket second, and then Corey third, Poop fourth, and Foo last. So if I wanted to find Foo, first I'd have to find the key value, which is this, 6, and when I get to the bucket that 6 hashes to in the table, then I'd have to go through these 5 elements of these other entries because my hash table, my hashing algorithm is poor. And then I'd have to, after I'd find the key that this hashed to, I'd have to go through all of these values to find the value of foo, which is 14 in this case. So that would be the worst time complexity for a hash table of O of n, assuming that every element that you hash to the same one. That explains the worst case. Anyway, so let's move on to the actual implementation, because I got ahead of myself, but whatever. So line 20, we have a constant called table size, which is equal to 128. So this means that we have 128 space hash entry objects that we are going to be able to take advantage of to use for our hash table. And then we have hash entry table, and I need to make a note. I just thought of it. What is it? Of the hash size. Oh, clustering and collisions. That will be in the put, so we'll put that next to put. Okay, so on 22, we have a declaration of an array of objects, of hash entry objects called a table, which makes sense because this is the hash table. Then we have a hash map, construction of the class, or a constructor of the class, and we're setting table equal to the new, a new array of hash entries with the table size, which is declared up here. So in this case, we're making a table of hash entries of 128 hash entries. So what we're doing here on line 27 is you're taking, you're iterating through your table, and you are setting each element of the hash entries to null. Because they're objects, you want to make sure that it's all empty so that you're not messing with anything that can mess up your computer or have a seg fault or any stuff like that. If you're interested in learning what a seg fault is, look up segmentation faults and you'll learn all about memory and interesting stuff like that. So moving on, we have a member function called gets. It returns an integer, and it's a public member function, and it takes in a key. So essentially what's happening is you have this hash, and you're hashing the key in the table size. Yeah, this is a very simple implementation of a hash table. Usually when you hash something, you want some kind of pseudo randomness to make sure that it hashes uniquely every time. So uniquely at runtime. So like, if you were to see a random number from the computer, you would take that random number that's generated at runtime, and you would use that random number to hash everything. So like, let's say if my name is David and the random number is 7, and then I don't know, I add 7 to the ASCII value of each letter of David. So like, David would turn into some weird thing. Let's see, ASCII table. So David, capital D is this. Oh, I can't do that. Okay. Capital D is up here, which is a decimal of 68. So if I were to add 7 to D, 7 is 75, so it'd be K. And then K, so K would be the first letter of my new hashed name, or my hashed name, I guess. And then A, so 65 and 7 is 72, so H, so it'd be KH, and then V. These are, I guess I'm doing all capitals because I'm from the 90s, but V7 and 86 is 95, 93, because math is hard. So we'd have KH, close bracket, and then I would be 80, P, KH, close bracket, K. So that would be my new hash, that'd be my new hash algorithm, or my new hashed name. So what I'm trying to explain is, plus 7 would hash to KH, close bracket, what was it? Something K. KH, close bracket, what's I? 7080 P. So let's say we hash that new name. You would want, so let's say the random number is 7, right? So the random number rand is equal to 7 in this case. So in another run, in another running of the hash table, you would get a different random number, hopefully. And so let's say in this rand, in this other rand, you would get 8. And then the same value of David would hash to UCEFT HI bracket carrots P Q and then L. So this isn't a very strong, this isn't like a real world application of what it would be, but the idea is that each time you ran the hash table, everything would hash to its own unique location consistently. So yeah, so that's off of that rabbit hole. Let's move on. So then, in this, we're iterating over the hash table to find a key. Oh yeah, because it's get. Okay. So because we're in the get function, what do you do in the get function? You get the hash entry object with the key value that you plug into it. So that means we're going to iterate, pretty much we're going to take the hash and we're going to iterate over the hash because we're using the hash as the element number of the table. So what this is saying is, we'll take the hash, let's say, in 6, let's just trace through what would happen. So we're printing out whatever return we get returned from map.get, which is an integer, right? Because this is returning an integer. And what happens is, let's say you have 6. Okay, so in this case, let's ignore these 4 previous integer trees, I don't know, jokes. So let's ignore that, let's look at these. So we put in a key value combination of 6 as the key and 14 as the value. When you try to get from the map whatever's at the hashed value of 6, what's going to happen is you go to the get function, and we're going to trace through this with a integer with a key value of 6. Okay, so let's say integer. So we're setting an integer named hash to the key mod the table size to this value, which if you have key mod 128, we're putting 128 into 6 until we get a remainder. That's what I'm understanding. So on line 39, we're setting an integer called hash equal to the key mod table size, which in this case is 6, because 6, this is correct, right? Because 6 mod 128 is 6. Okay, so then what we do is, while we have the table, and the hash is equal to 6 now, right? So the table element of 6 is not equal to null, and the tables of 6.getKey is not equal to the key. We are going to take the hash and we're going to increment it by 1. So in this case it'd be 6 plus 1 hash, and then 6 plus 1 mod table size, and then you'd keep doing that until you find something that is empty and the key is not equal to the key. The element is not equal to the key of the hash entry that you're trying to put into the table. Wow, this is ridiculous. So moving on, what pretty much what this is doing is it's iterating over the hash table to find the key that you're looking for. Okay. Oh, because this is the get function, not the put function. Wow. Okay. So you're iterating over the hash table until you find the key that you declared that you're looking for up here. Okay. So then, if you iterate through the whole thing, so this while loop is going to go until you reach table size. Until you reach, you've iterated over every possible elements in the table, okay? So this means if the table's elements of hash is equal to null, return -1, meaning the key that you're looking for does not exist because we iterated through the whole entire table and we couldn't find the key that you're looking for. And then with the else, this is saying so let's say you find the key in this while loop, you would jump out, and because you found the key, that means there's a value there. So that means that this, the table element of the hash is not empty, which means that it's not this. So you would jump out of this, out of the if statement, and jump into the else statement, and you would return the integer that is found by the table's element's hashed value. Wow, this is crazy. Okay. You return the table element that you're at, that element's value, because that's what the key hashed to. Okay? I hope that makes sense. I hope that makes sense because I'm moving on. So, with clustering and collisions, I wanted to talk about this because this is really interesting. When you think of a hash table, you would want it to be, you want to think about it in the sense that, well, in my head, this is how I think of it, think of it as a straight line, okay? So a hash table has all of these elements that come down to table size or nth elements, okay? So if you have a full, an empty table, okay, and this is bothering me, so if you have a whole table, right, and it's a straight line, and when you put an element into this table of the straight line, let's say that it bulges out a little bit right there, right? So like you have a table, which I'm going to draw sloppily. Imagine you have a straight line, okay? So you have a straight line, and what happens is, let's say you put something at bucket 4. So now this little teeny bump is going to come out. I hope you can see that. There's a little lined bulge here to indicate a bucket was filled, okay? So you have this super straight line that isn't curved at all because I'm an amazing artist. Every time you put an element into a bucket, you get a little bulge, right? Because you love computer science so much. Wow, jokes. So then if you think about it, assuming that your hash table implementation is made correctly, let's say that what you're going for in a hash table is you want even distribution over the entire hash table so that collisions don't happen as often. Because if you think about it, I'm just going to draw some more buckets real quick. Because if you think about it, if you have a well implemented hash table and you have an even distribution of elements and buckets, over time you would have what is essentially at least a wavy line, but at best another straight line, right? Because if you increment this is a theoretical thing that I just want to get off my chest because I feel like it's really interesting. If you get a nice little an infinite amount of table elements, which is ridiculous because infinite memory doesn't exist, and there's crazy implications and stuff. But assuming that you have nth elements and there's an even distribution along your table, you would eventually end up with what is I guess technically a straight or a wavy-ish line. So you'd have this even distribution, right? And what you want within your hash table is an even distribution, because if you have a hash table that is implemented poorly, and you have an implementation of the hash table that is on running time, or on insertion, deletion, and search, as indicated here. If you were to run into on time, worst case of a hash table, run into something like this, right? And this is what sucks about this. Assuming you could read that. So what sucks about that is that's a representation of a hash table with on search, insertion, and deletion, because there's no access, because it's all. Anyway, so what sucks about that, what would suck about that is, let's assume that you have, this is just another example of the on, but you get to bucket 4, and there's a giant mound of it, of elements. You would have to look through n, I guess n plus 1? Well, sure, let's just say n plus 1. You'd have to look through n plus 1 elements to find whatever's in your bulge at bucket 4, okay? And that sucks because that takes away from the whole reason that you're using a hash table in the first place. You build a hash table for the constant lookup times because that it's beneficial to whatever you're doing, whatever the data structure, whatever database or usually hash tables are just used for databases. I can't think of another example of where you'd want to use a hash table that isn't ridiculously small or inconvenient. Yeah. Anyway, so if you think about clustering, so that was collisions. That was an explanation of collisions and poorly implemented hash tables. So then if you think about clustering, as indicated here, because we need to talk about that. Let's say you have bucket 7, and 8, and 9. This is a very small hash table. So if you have clustering, which this is poor, if you have clustering like this, and what you're looking for is in bucket 7, let's say a lot of, or in this case, 3 elements hashed to bucket 7. So then this means that when you get to bucket 7, you're going to have to, okay, I'm just all over the place, I'm sorry. So let's use this as an example. We have David, Lisa, and Corey at bucket 7, 8, and 9, and we all hash to the same spot for whatever reason, one way or the other. And what sucks about clustering is that if you get a clustered, if there's a spot in your hash table that's clustered, and you have, let's say you have 3 elements, David, Lisa, and Corey, right here, that hash to bucket 6, I guess, in this case. We'll use 7. We'll think of it as 7. So, that didn't work. So, we will discard poop and foo for the moment. Let's say you have all these elements that come to, that hash to bucket 7, okay? Then, in your put function, you have to account for having an adequate table size that accounts for the amount of space that you need, as well as collisions and clustering. Just think of it as clustering. So let's say in this particular instance, we have bucket 7 that clusters these 3 inputs of David, Lisa, and Corey cluster around 7, and my cluster of collision resolution promotes clustering, I guess would be the best way to think about it. If I resolve collisions by saying, oh, if there's something in this bucket, just move over one and then put it in that bucket, assuming that it's empty. What sucks about that is if you have for some odd reason, a bunch of elements hashing to, or a bunch of keys hashing to the same spot, then you have to go n plus whatever, element plus n, or n plus whatever, in this case it would be, or n plus c, I guess, because it's constants, but the constant changes. In this instance, we would have to, let's say we have to find whatever's in bucket 9, okay? And because of my poor collision resolution algorithm that lends itself to clustering, we have to search now. So let's say I have to find Corey. So we have to go, we say put, or get, I think it's key value, so it wouldn't be the same, but let's say you do something like this. And let's say, yeah, okay. Let's say for whatever reason, let's say in the put function, I say something to the effect of hash is equal to 7. This is just saying we're going to go to whatever the hash 7, whatever element in the table at element 7, and we're going to put all our stuff there, right? If the resolution for this collision, because there's going to be collisions, there's going to be tons of collisions, you would have to, let's say the collision resolution would be, if it's occupied, the space that you're looking at, that hashes to 7, then move hash element, table hash plus 1. Because you would want to move over to find the next possible empty hash entry object to put your new entry object into, right? So if you have, again, this example of you have David, Lisa, and Corey, and they hash to the same value, and your collision resolution is move over one and put that there at the next possible space. The problem with clustering is then you'd have to find, if I wanted to find Corey, and because Corey hashed to 7, in this case, to 7, you'd have to find, when you go to the get function, you would have to look through n plus 2, because n plus 2 spaces, because if you get to the 7 and there's already something there that is not Corey, which in this case the value associated with Corey is 12, right, because this is the value spot of the put, right? So if you're looking for the value of 12, because you have a search for value instead of search for key instance for whatever reason, because that's not entirely practical, but let's say for the sake of the example, you have to look through, you have to look and find Corey with the value of 12. What happens is when you get to the bucket number, the bucket that hashes from the key value of 7, then you have to look through 7 and the next one and the next one and the next one until n plus whatever the hash table element is plus n to find whatever you're looking for at Corey. That's bad, because you're losing out on time, and this is ridiculous because it's such a small scale. But imagine if you had a poorly implemented hash table that hashed 50,000 elements or 1,000,000 elements to this this cluster. That means you're going to have to look through n plus a million for, let's just say, the millionth term from n. The n plus millionth term is what you're looking for. That's a million extra searches that you had to go through. So it'd be n constant. So it'd be log 1 plus million, which isn't crazy, but it's significant, because if you have to, let's say a search is 1 and constant time is constant time, but let's just assume that you have to, well, each search costs 1 second. If you had to wait a million seconds to find your element in a hash table, that is a terrible hash table implementation. But that's the point of, that's why clustering is bad, because you'd have to look through n plus however many are in the cluster to find your element, which is just a poorly executed collision resolution. But that's pretty much the end of that rant of clustering and collisions. So moving on, let's say we go back to this, or not that. So we're taking the hash, and this is for the put function. We're taking the hash, and we're going to search through the table until we find both something that is empty, because the opposite of null is occupied. You want to find a space that is empty, and that the hash is, the table element's key is not equal to the key that you already have. Yeah. Then you would iterate through the whole entire table until you found something that fulfills this, and you would exit, and then you would set the new table, the table's hash equal to the constructed entry of whatever the values are that you send. So in this example, because that took a while, this is going to be a long one, guys. I'm sorry about that. So in this example, you have put, and you would put, oh, let's do some fun stuff. So 7, oh, not that, 7 words, 7, 8, 9, or 0, or 9, and then let's do it again, and we'll replace it with 19. So what would happen if you have a hash table, and, oh, you know what, we're going to do this because clarity, or formatting. So what happened on line 74, so let's just establish that 70 to 72, you're putting in hash entry objects with a key value of 7 to 7 and the value of 10, key of 8 to 11 with a value of 11, and the key of 9 with a value of 12. So when you get the key value of 6, there's nothing there, which means that it's a null, which means it should return -1, right? Because nothing should be there, because we didn't put anything there. There's no put function with a 6, because there's no put function with a 6. So now, if we print out whatever's at 7, we should get 10, right? Because assuming that the put function works correctly and the get function works correctly, when we search for the key value of 7, we should iterate through the table until we find, or iterate from the hash of this value and find the value of this. So we should find 10, 11, and 12 respectively, because 7 is with 10, 8 is with 11, and 9 is with 12. And finally, just like on line 74, if we try to get something from the map that doesn't exist, it should return -1, as shown here. So if the table's element hash, if the table of the element hash, so if you iterate through the table, you don't find anything, and whatever the last value of the table is null, because there's nothing there, you would return -1 because it doesn't exist. So let's make sure this works! Words, okay. Java, C, hash table, Java, and Java hash Cool. Okay. So this makes sense, right? Because, as we said, this should print out negative 1, 1, and 7, and then 8, and then 9. I mean, not 7, 8, 9, 10, 10, 11, and 12, and then negative 1 again. 10, 11, so negative 1, 10, 11, 12, right? Because those are what are in those key values of the table, of the hashed key values in the table. Yay! So I hope you learned something from this. This has been fun, and this is a long video. Wow. I need to go do my laundry. I need to go dry it. So I will see you guys in the next video. I hope you enjoyed watching this one. If you didn't, dislike, and if you did, like it, maybe. And if you really liked it, you should subscribe to keep watching me rant to computer and a camera, because that's fun. Yeah, okay. I'm gonna go do laundry.